So we have a galvanic cell, and it's got two half reactions, and they're given here. And then it asks us what is the E cell if we have specific concentrations of these. So this is our hint, the fact that we have E cell with no standard symbol, and we're actually given concentrations, that we are actually going to need that Nernst equation. So oftentimes what can be best is to just go ahead and write the equation so we can actually look at all the parts and think about where we need to go. Because we really only at this point have one equation that will tell us something about the E cell, and that also involves concentrations. So based on what we know, we've got all the information we should need to figure out E cell. So we can figure out E cell by using the standard reduction potentials that we've got. And R, T, and F, those actually are all constants that we can look up. We don't have a temperature given, so we're going to assume that this is 298 Kelvin. Q, we're going to have to actually figure out the Q expression. So this is also going to take us a little bit of work. So this is going to have a lot of different parts to it, but it's absolutely doable. But it's one of those things where we need to look at this one thing at a time. So let's go ahead and start with E cell, standard. So in order to actually calculate the standard E cell, what we're going to need to do is look at our reduction potentials. So first of all, they gave us both of these as reductions. So these are the same exact way they would be if we looked them up in a table. So you could have a table like in the back of your book that is huge. This is actually the one you might notice from the exam last spring. So from spring of 2015 is when this one's from. And it's just a huge table. So we might be able to give you this huge big table, in which case you could look them up. This is also where I would recommend getting another piece of paper so you could actually have a line across. You could actually tell, because it's really easy to take your pen and go and miss the right one. So you might look it up in a table. But in this case, they actually gave us both equations. So since we have both equations, we don't actually need the table. All we actually need to do is figure out which one of these is which. On the table, what you would have found is that most people are pretty good with the fact that if I've got a table, at the top I've got positive values, at the bottom I have negative values. So usually as I look towards the top, I have reduction, and as I look towards the bottom, I have oxidation. So that makes the table relatively easy to read. But again, we don't actually have a table in this case. So what we actually need is we need the fact that the more positive one will be our reduction, and the more negative one will be our oxidation. So we can look at these two values. They're both negative, but this one's less negative. So this should actually be my reduction. This should be my oxidation. So now that I have that figured out, I can go ahead and figure out my E standard of the cell. Now I'm going to use the equation that I like, which is the fact that I'm just going to add these together. I know the book does something different. You can find the other equation somewhere else, but I'm going to do it this way. And what I know is both of these are actually reduction potentials. So these are actually reduction potentials because they're set up as reductions. So I get to use one of those exactly as is, but that other one, I actually need to switch the sign because it's written the wrong way for what I'm actually looking at. So I do need to go ahead and take one of those and change my signs. And that way, when I do that, I get my E standard for the cell as 0.49 volts. So I have my E standard for the cell. So I've got one of my components. So far, so good. Next, we can go ahead and take a look at this R, T, and F. And you'll also notice we have an N there. But let's go ahead and look at R, T, and F. So for those three, those are all going to be things that we can pull off of that potentially useful information page. So they're not things you need to memorize. But you can find R, and you can actually also find F, or your Faraday's constant. So we found F, it's hanging out right there. R, you notice we've got two options for it. Even though this says Coulomb per mole of electrons, Faraday's constant's also related with coulombs and volts and joules. So when you're coming down and looking for your constant for R in this case, you're going to use that one. So that then turns into a very lovely plug and chug. So I've got my E standard for the cell. I'm going to have a value of R of 8.314. That's going to be in my joules per mole Kelvin. I'm going to have a temperature of 298 Kelvin. It didn't tell me otherwise, so I'm just going to go ahead and assume that. And I'm going to have a Faraday's constant of 96,500 coulombs, also per mole of electrons. Then I have this N that I've got to work with. So N is usually moles. In this case, this is actually supposed to be moles of electrons. So in order to actually figure out moles of electrons, I need to look at my equations. Because what I need to find is how many electrons are being transferred in this reaction. Well, that brings us to these guys. And when I look, I see I've got 2 electrons in one place, 3 electrons in the other. If I was actually going to add these two together, what I would actually do is I'd multiply one of these times 3, by the other one times 2. We would also reverse this guy. We'll do that in just a moment. So what I can see is that in order to get my N, what I should actually have is 6 electrons. So in order to get my N all the way down here, my moles of electrons, that's going to be 6 electrons. So I'm glad that you guys spent time balancing redox reactions, because this notion up here, you don't necessarily have to do all of the balancing in order to figure out how many electrons you need, but you need to be familiar with, my goal is to get my electrons to cancel, so that's what I'm going to do. I'm going to do something to get my electrons to cancel, and so I need 6 electrons in order to make this equation work. And sure enough, down here for our N, 6 is what we have. So that'll get me through E standard of the cell, R, T, N, and F. So we're doing really well. Now we come to L and Q. So this is the thing that we now have left to do. Natural log, this is just a button on your calculator. So that's not a constant, that's not anything else, that's just the natural log. But now I have Q. Well, Q is based on products and reactants. Well, so far I've got 2 half reactions. So what I actually need to do is actually figure out what Q is going to be. So what we actually have to do is take a look at what our reaction will be, which means at this point I need another piece of paper. So to figure out Q, I actually need products over reactants. So Q has been products over reactants and raised to their exponents. That's right, we've got to actually figure out exponents. So I'm going to go ahead and rewrite these. So I have my nickel for reduction. So I'm going to have 3 nickel 2 plus 6 electrons goes to 3 nickel as a solid. My chromium, remember, this is actually reduction, so I need it to go the other direction. So I'm going to have chromium as a solid. There's 2 of those going to 2 chromium 3 plus 6 electrons. So what you should see at this point is that whatever my reduction was, my reduction is going to have my aqueous species in the reactants. My oxidation is going to have an aqueous species in my products. So when I actually add all these together, I get 3 nickel 2 plus, my electrons cancel, 2 chromium as a solid, 3 nickel as a solid, 2 chromium 3 plus. And for our Q expression, I don't actually care about these solid components. I know we took all the time to write them out, but we don't actually care. So what I do care about is I do actually care about the aqueous species. So as far as my Q is concerned, I just need my products, my chromium squared divided by my reactants, my nickel cubed, and that's Q. So now I can look back at my original question that actually gave me values for those. So for Q, I can go ahead and plug in for chromium, 2.0 times 10 to the negative 3 molar. That's from the question, all squared. divided by nickel, 1.0 times 10 to the negative 4 molar cubed. And I can get a value for Q. After we do some simplification, we get a Q value of 4 times 10 to the positive 6. So now we actually have everything we need. So now we're finally actually to a plug and chug question. It's just got a lot of pieces and a lot of parts. So now all we need to do is we can actually go back to our equation. There we go. Our E cell equals E standard minus RT in F, L in Q, and just put in all of our numbers. Great. So E cell equals my E cell standard. Where did that one go? E cell standard is 0.49 volts. Minus, this is where now I have that RT, so I'm going to have that 8.314 times my temperature divided by the number of electrons times Faraday's constant times the natural log of Q, which is 4 times 10 to the positive 6. So we'll get a lot of simplification. So after we do all of that lovely math, we have 0.065, which will give us a grand total of about 0.42 volts. So the Nernst equation is a plug and chug, and the nice thing with Q is that we've been doing Q. It's been a little while, but we have done Q before, so just to remember that you still have to take into account your exponents. And then otherwise it's down to a bunch of constants. So again, there's a lot of components, but with some practice, I know you guys can get this.